Today is lesson 2.7. It says we can combine functions to create a function composition. This is the word here, function composition. It means really what we're doing is we're putting one function inside another function. So if you look on your next slide, it says a function composition is applying one function to the results of another. Mathematically, it's going to look like this. Either of these two symbols. You could see it this way, or you could see it this way. They mean the same thing. So PEMDAS question for you. According to PEMDAS, if you're doing order of operations, I want you to focus on this one for a moment, right here. Where would you begin? On the inside or the outside?
The inside.
You'd begin with the inside. So you'd be looking at the function g first. Your input would go into g, and then whatever the results are of g, you apply into f. So the way I did it, the way I'll draw it is like this. Let me take this off here. The way I'll draw it is like this. You'll take an input value into g, and you'll get some y value result. That y value will become the input value into f, which will finally produce some new y value that'll be our answer. This will produce some new output value that'll be our answer. Okay, so I have the arrows there. Let me scroll down, and here this is walking through the same thing, that I'm plugging something into g. So x of g, a domain value of g, you plug into g and it'll produce some new y value. Well, this y value becomes the x value into the f equation. That's what this is saying right down here. And once you plug that into f, you'll get some new y value output. And that's the order that we're going to do this. Okay, so getting started here with this slide here. How many different ways can we write composite functions? How many different ways did I just say there would be? Two. There are two ways. So you could see it as FOG, like that. And by the way, that's a composition of two different functions, f and g. You can have more than two functions, by the way. You could have 3, you could have 4, you can have infinitely many. Oh, God. There's another way we can write this, and it's like this. Either way, how do we read these expressions? You'd read it as f of g of x. That's how you'd read that. F of g of x. So one more thing I've said already, but we're going to now fill in the notes. When working on composite functions, we follow what for our order of operations? PEMDAS. And what does PEMDAS mean? You start with your parentheses. So starting with parentheses, it's helpful not to necessarily look in this way of writing it, but this is the same as this. We evaluate which function first. So x is the input, so you can't evaluate the input. G. You evaluate g first, and then we'll use the answer from g to plug in there. You got it. There's your step. So today as we go through, I'm going to show you these in a multitude of different ways, a variety of different representations. We'll show it through by table, using circles, using functions, using numbers. I'm going to show you all different ways we can do this. Okay, so getting started. Let's first look at using circles. It says, given the functions f and g, find f of g of x or f of g of x. You would read those exactly the same. They are one and the same thing. So where do I begin? You would begin with g of x. We're going to start there. We're going to plug in values into g and then plug those g values into f. It's the same thing here. You plug into g and then take g's results and plug them into f to get your final answer. Okay, so I've already plugged these in. So these all get plugged in. These are my input. These are my x. This is my y. So what do I do with these y's? You plug them into f. So I look over here. Do you see we have a -3 in common? So draw a line from one to the other to connect, from -3 to +3. Go ahead and do the same. What about -1? Do I have a -1? No, so that would not make it, that would not make the final domain and range. What about a 0?
Yep.
I have a 0. What about a 4? 7?
Yeah.
Okay. So what does this mean for our function of f of g? What it means is this. Oh, I forgot to put the y over here. The only values you'd copy over into the domain are the values that produce, that we're able to go from g into f. So what produced a -3? A 1. What produced a 0? -5. So -5, 1. And what produced a 7? 0. Those are the only values that make our domain. -5, 0, 1. Those are the only 3 values that make the domain. So what makes the range?
Resulting one, so like wherever the -3 connects to, so
Alright.
goes to 5.
5 would make it. 1 would make it, and 7 would make it. 1, 5, and 7. Now, if you wanted to, you could connect -5 should be pointing at 1. So -5 should point at 1. Now, wait, why am I saying that? Because this -5 produced a 0. 0 got plugged in and produced a 1. So -5 points at 1. Okay, what will 0 point at?
No.
No. 0 will point at 7, and that means 1 must point at 5. This domain, go ahead and put this note on there. The domain is a subset of the domain is a subset of, now, where did these numbers come from? -5, 0, and 1. Where did we originally get those? G's domain. Okay, so the domain is a subset of G's domain. Where did the range values come from?
The output.
The output of f of x. So the range, the y values, the range is, whoops, is a subset. That's not, got dyslexic there, sorry. Is a subset of f's range. Now, subset doesn't mean it's always going to lose numbers, but it does tell you that it won't gain any numbers. So it's only going to be coming from here. It won't gain any, but it won't. It could lose some, but it won't gain any other values that are not in f's original range. Okay, that's what it means by subset. I'll go ahead and highlight that. That's the key word there. Subset is a key word to understand. Okay. With that, I have a DOL for you to try. I'll let you do this one. Okay, example 2. Let's switch gears. What if we looked at this using equations? I have 2 parts here. Find g of f, and then we're going to find f of g. And we'll determine, do we always get the same answer? Will we get different answers? What can happen? So first, let's go with g of f. Where do I begin? Do I begin with the function g or begin with the function f? F. Everything gets plugged into, I say everything. We plug in x here, and whatever we produce out of f gets plugged into g. Well, are we actually plugging in a value into f? Like, is there a number there or anything like that? Since I'm not plugging in a number, what I'm going to do is take this equation and plug it into g. So again, the way you could rewrite this as g of f of x like this. So here's how I'm going to rewrite it here. G of f of x. Here's how algebraically it should look. I'm showing you here with perfect algebra. You would take this g equation, But instead of plugging in the domain x into G, what do we replace this x with?
The equation. That's
That's right, because we're gonna replace that. So instead of an x, that's where I'm gonna replace it with 2x minus 5 plus 1. So that's G's equation with f's inside it. Now that's like the pure algebra right there. A way you might hear me say it also is a technique I like is to stack. I think sometimes it's easier to stack and see it this way, is I will stack from the first down to the last function in that order. And the reason I like this is because you can visually see it a little bit better. What we're doing is we're taking this entire equation and we're substituting it into x, because the idea is we want to stuff this f of x into x. And a lot of times I'll write it that way so that you can see what's happening in that regard. You see how I still get the same value right there? So this is just a technique. I call it a stack technique. If that helps you, all power to you. But what I have, technique is with Q, right? What I have here is the pure algebra. Okay, so how would you solve that pure algebra here? Distribute. So what's 3 times 2x? 6x. What's 3 times negative 5? And then we add 1.
minus 14.
So 6x, negative 15 plus a positive 1. I agree with Jonathan. He said negative 15 plus 1 is negative 14. And if I want to rewrite it their way, you could use the brackets g of f of x. You could write it that way if you like. But there's your answer. All right, let's see if we get the same thing if we plug this in as f of g. Let's see if it's exactly the same. So what's another way we could rewrite f of g? And I heard you say f times. Actually, this would be substituting is really what it is. It's substitution. We're substituting the function g into f's equation for its domain. Okay, so again, using perfect algebra, it would look like this. Using perfect algebra, it would look like you take f's equation, but when you come to the x, what do we replace this x with? 3x plus 1, and then we'll minus 5. Yeah. So what do I need to do again here? Distribute. So what is 2 times 3x? 6x. What's 2 times positive 1? And then we subtract 5. And here we'll get our answer. To write it in their symbols, this would be f of g of x. This would be 6x. What's a plot? Positive 2 minus 5. Do we have the same answer here or different answers?
Different.
So the answer is not the same. So on composition, order does matter. Why does it matter? Because it's not purely multiplication. Just to clarify one more time. I know we use the parentheses to mean multiply, but when you're writing it out as a composition, it truly means substitution. If it were multiplying, it would not matter the order. Just think about it. What's 3 times 5? 15. Hey, say it with me here. 3 times 5 is? 5 times 3? 15. The order matter. 8 times 2? 2 times 8. Does order matter? So when you multiply, order does not matter. This is not purely multiplication. Okay, it's substitution. That's why order does matter. It's substitution. Maybe we ought to make that note up at the top. Truthfully, this is substitution. Substitution. So if you want to think of what does a composition truly mean, it means to substitute. Okay, and again, you could use stack technique if that helps you out. Again, that's just a technique, something to help you accomplish the task at hand. But what I have written up the top is writing out truly perfect algebra way. Not that makes it better. Okay. All right, let's do a couple more. This time, what if we wanted g of f of 5 and then f of g of f of 3? How would we do that? Well, let's start with here. So using arrows to help us understand what to do, we're going to plug 5 into f and we'll get some new output. And what will we do with that output?
Plug it into G.
We'll plug that into G. That's right. And that'll produce some final answer. I'll just do A and S. That'll produce some answer. That's what's gonna happen there. We could rewrite this, by the way, as G of F of 5. You could rewrite it that way. Okay, using pure algebra. Here's how I'd write this out. Pure algebra, you would start with the G equation. Start with the G equation. And what do you do when you come to the X? You put a parentheses and you would insert into F's equation. But when you come to the X and F's equation, we would pause and say, what goes into this X? 5. Now this is where it can kind of get confusing for some students. It's like, wait, where did I stop? Where do I pick up? But just writing it out, it'd be 2 times, instead of X, I'd do a 5 minus another 5, close your parentheses, plus 1. Now you can start seeing when I'm writing this out how this can get confusing. And I'm only doing composition of 2 functions, not 3 yet. So this is where stack technique can really come in handy. Again, let me just do a stack technique here. Why stack can be helpful for you is if you write out your equations, you start from the left and work your way to the right. 3x plus 1. F's equation is 2x minus 5. And then the x value, what are we saying x is? 5. Now, why this can help. So what we're going to do here is I substitute going up. So this 5, whoops. Try this again. This 5 is going to go here into this x. And truthfully, it's going into both x's. So what would I get here? I would have 2 times 5 minus 5. What is 2 times 5? 10. And then minus 5 more? 5. Now, before I write that, look where, you see how that's exactly the same as what I have written right there? But sometimes writing it in stack, it's easier to make sure you get it right. So we said 2 times 5 is 10, minus 5, we got a value of 5, which means I'm now going to plug 5 in right there. Because what I'm now doing is I'm plugging in f of 5 into here. So what do we get? We get 3 times 5 plus 1, which is how much? 16. And that's going to be your solution right there. Now it's the same thing here. If we did PEMDAS, we'd start with this parentheses. 2 times 5 is 10 minus 5, 5. So we have this parenthesis equals 5 right there. If you simplified that, that parenthesis equals 5. So 3 times 5 is 15. Add 1. Notice we still get 16 either way. Still get the same answer. I'll let you decide what you think is easier. All right. So this one, again, I'm going to do pure algebra first, and then I'll do stack technique. What do I do this time? I plug 3 into F. Plug that into G, and then plug that into F once again. So if I were writing out pure algebra, I would start with the F. I'm just going to start plugging into the equation. F's equation is 2x minus 5. So when I come to this x right here, what do I place inside that x? G's equation, which is a 3 followed by another x. Now when I come to this x on G's equation, where do I go to now? F, which is another x.
No, wouldn't you do it 3 at the start? That's F's equation.
Yep.
J's equation.
So if you're writing it out with pure algebra, you would write it out. You start with the outside and work your way in. Does that make sense? So let me go ahead and write that one more time. So obviously we have some questions here. So let me do this again. This is where I'm trying to get to. Stack technique can really be helpful, especially when the compositions become more complex. So you see all these different parentheses I'm going to have going? F, G, F of 3. 1, 2, 3. You see all these different parentheses? We're gonna have a lot of craziness going on. So you start with the f, which is 2x minus 5. But instead of the x, what am I gonna put in place of x?
G.
G, which is 3. But
G, you're gonna plug into the equation.
instead of the x of g, I want to now put in f, which is 2 times. But instead of this x, what am I going to replace inside of it? 3. And finally, we get a close of parentheses. So I have my 3 open parentheses. And I close one. So I just closed this where I put the 3 in. So what comes next? Minus 5. I get to close another parenthesis finally. So now I close this one. I'm back over here. Plus 1. Close another parenthesis. And minus 5. That's how it would look. Now that's pretty tricky. Would you not agree with that? That can be pretty tricky. Again, once it gets complex, I'd recommend you do a stack. Using stack, it takes away the trickiness of it. So what was F's equation one more time?
F's equation is 2x minus 5.
2x minus 5. You just stack that on top of G, which is what was G? 3x plus 1? What was F's again? I just gotta look up. What am I thinking? 2x minus 5. And then underneath that, we would have an x value of 3. So how I would start doing this is I'd plug this x in there. Truthfully, I'm plugging into, so I'm finding f of 3. So what is 2 times 3 minus 5? Which if you check that out, that's the innermost portion right there. That's what I'm finding right now. 2 times 3 minus 5. What's 2 times 3?
6.
And we subtract 5. 1. You see how we just got 1 there? So now what do I do with this 1? We're going to plug it in right there and right there. So now I'm finding G of 1. 3 times 1 plus 1. What is 3 times 1? 3 plus 1? 4. So that was 3 times 1 plus 1. All of this section, from there to there, we got 4. That all equals 4. So now we take this 4 and we plug it into, we're now finding f of 4. So it'd be 2 times 4 minus 5. And you don't have to do all these arrows. I'm just showing you clearly what I'm doing. 2 times 4 is 8 minus 5. You get a final answer of 3. That would be your answer there. And so if I plugged all that in, 2 times 4 is 8 minus 5. Yep, still get 3. I'm running out of space there, so I'm just do it right there. 3. So as you get more complex with your functions, I would definitely recommend stack. You don't have to use stack, but I'd recommend it. Which takes us to our second DOL. All right, your turn. I want you to work through these two. Now let's talk about restricting the domain. Sometimes the domain of a composite function may not be the same as the domain of the original functions. The domain of the composite function will always be a something of the domain of the innermost function in the composition. It's always a what? Subset. Put the word subset here. It's always a subset, which means it might not be the same, but it'll be taken from the innermost function. Now, the range also might be restricted. Additionally, the range of the composite function will always be a subset. Now, will it be of the innermost? Outermost. It's a subset of the outermost function. And you can look back at example 1 for that illustration that we did. Okay, now that we've filled in our blanks, let's look at our next example here. Given these two functions, find g of f of x and state its domain. So let's just start with the obvious here. The domain of f, is it all reals? Do you see, remember the three things that can eliminate a domain is division, you can't divide by 0, a square root, can't take a square root of a negative number, and a logarithm. Logarithms must be positive. Do I have any of those three symbols here?
It's not a negative. Means that the exponent.
Inside the square root. What's the rule on even roots? They must be positive or out of the three types of numbers.
Equal to 0.
It can be equal to 0. Can it be negatives? No, it's got to be. So it can't be that. So what can be is 0 or positives. That's a square root or an even root for that matter. So the symbol here is you'd say x minus 3 can be greater than or equal to 0. So what does that mean the domain of f is? That's right. Now over here, is this all reals or not all reals? This is all reals. That's for the function f. Let me just do f here. This is for the domain of f. This is the domain of g. It's all reals. Now what are we trying to find here?
The domain of G of F.
G of f. So it's going to come from the innermost. It'll be a subset of this. So here's how I do it. Using stack, I think it's much easier. So with stack, and there's a reason I like stack. If I were stacking them up, what would I put on top?
Equation.
You'd put g on top, which is 2x squared minus 5. Now what's f's equation? X minus 3. I'm doing stack here, just to be clear. I'm using stack technique. Now, the way it works is once you eliminate a number, the number can never come back. So for this domain, at this stage, the domain is already limited. What are we saying the domain is limited to? It's greater than or equal to 3. Now, why is that important? Because when I plug this in here, as I substitute f's equation up here, we get 2 times, and in this parenthesis, actually I don't have to use a parenthesis because this has a root, so I'll just use the root, x minus 3 with the squared there, minus 5 on the outside. Notice what I did is I just plugged this in right there. This is nothing different than if I had written it as g of f of x up here like this and started with g's equation, and when I came to that x, put in the square root. So there's the question. Can we cancel a square root with the exponent of 2? Are those opposites?
Yes.
Yes, so we can cancel those. Those simplify. So when I rewrite this, I will use parentheses in this time because the root is gone. So I'm going to say 2 times x minus 3 minus 5. So what is 2 times x? 2x, and then it'll be minus, and we need to minus 5. So the final solution here,
2x minus 1.
2x minus 11. Now that's our composition. That's g of f. That's g of f right there. Now, the domain, when you look at this, if you haven't already done, this is why I like stack, because what you do is you find the domain at each step. Would this lose any domain values? No, that looks like it's all reals, but it's not all reals. What's the domain? It's already restricted. It was restricted at this previous step. We have a restricted domain, which means even though the function 2x minus 11 itself would be all reals, we have a restricted domain, meaning the domain is limited. What is the domain limited to? X is greater than or equal to 0, or you could do, greater than or equal to 3, or you could write it this way, 3 comma infinity. I'll write it both ways. And you write it this way or this way. So our domain has been restricted. So if you want to know the domain, the range, you could start plugging in numbers. This is a increasing, decreasing, or constant function. What could you tell me about 2x minus 11 if you graphed it?
It would be a straight line.
Always increasing. What's the minimum value? You plug in a 3. What's 2 times 3? 6 minus 11. Yeah, if you plugged it in, we could find its range if we wanted to. The range, if you wanted to, you could say the minimum would be 2 times 3 minus 11, which is 6 minus 11, which I'll say that is -5. And since it's always increasing, it would be -5 into infinity. It doesn't ask us to find that, but you can plug in there to find that, which is a subset of this function. If you graph this, the minimum here is -5. That's the minimum. These numbers would just make it get larger. So the range doesn't lose anything. It's not restricted at all. It's actually the entire range of G, but the domain was restricted from F. Okay, so again, this looks like it should be all reals. Was it all reals though? No, why not? Because of F only could take certain values. And I'm going to show you that graphically here in a moment. Let's look at, oh, no, the graphing part comes right now. So do y'all want to do this on Inspire or Desmos? How do you want to see it? Desmos? All right, open up a Desmos. By the way, I attached a calculator that does this for you. It's already programmed in on Google Classroom, but for now I'm going to just type them in because I gave you the steps right here. Using technology to see that, what you would do is you would list in your functions. Doesn't matter the order. So our function f of x, if I remember, was the square root of x minus 3. Was that it? Okay, it says graph the function f of x. Graph the function g of x. What was g of x's equation?
G of x is 2x squared minus 5.
Okay, now remember what I was pointing out. The domain of function f, this is the innermost, starts at 3 and goes to the right. So our final domain will be a subset of that. The range will be a subset of the outermost. This is the outermost. What was the lowest this range ever got? -5. And so that was the smallest it could ever be. Now, to find a composition, you type it into Desmos or Inspire, which I gave you the instructions on how to do that. So we're looking for G of, G of f of x. That's what we were looking for. Now notice, here's the graph. Does that match the slope 2x minus 11?
Yeah.
Did that match up?
Yeah.
So we got the right answer. You see how those graphs match up? Why is it that G of f of x only starts at 3 though?
Because we have a restricted domain.
We have a restricted domain. It goes off of this domain. You see how the domain is about the same? Not about the same. It is the same.
Yeah.
But the range, is the range the same as the innermost? No, where does the range come from? The outermost. And how low did this one go? -5. So how low did this graph go? You see how that works?
Yeah.
So graphically, it can help you out. So if yours isn't graphing, it's because you didn't label this F and G. So I was looking at students that was not getting the same thing as me. Notice if I don't type in those names, it won't show you this graph because the calculator doesn't know what G and F are. So if you're doing this at home, make sure you name your functions. You see how I named f of x right there, g of x there? See how I named them, f and g? That way the calculator is programmed. It knows what to do with f and g. So that's how you do that, how you can check using technology. And you can do it on Inspire. I told you what to do here. Instead of titling f and g, you call it f1 and f2. And then here you'd say f3 equals f2 of f1 of x. Make sense? Yes, no?
Yep.
All right, let's do another one here. All right, so this time we're looking for K of P. Let's type these in and see what you get. Algebra first, calculator second. Algebra first. All right, so if it says K of P, if I'm using stack, if it says K of P, what function do I put on top? K. So K of x is x squared plus 4x plus 5. By the way, is that all reals or not all reals? Do you see any divisions of x's? Do you see any square roots with x's? Do you see any logarithms with x's? It's all reals. What about over here? Will this be all reals?
Yeah.
Do you see any divisions with x's? Square roots with x's?
Square root.
Square roots with x. What's the rule of square roots? Square roots cannot be negative. That means the inside, the 3x plus 1 must be greater than or equal to 0. This domain will be different. It'll not be all reals. Let's do some mental math. This means that x will be greater than or equal to, how do you get rid of a plus 1? Minus 1. How do you get rid of a multiplying by 3? It'll be greater than or equal to negative 1/3. That'll be your domain here. Okay, so there's k of x. We put p of x underneath it. Square root of 3x plus 1. I'm going to go ahead and write off to the right. We already found the restricted domain. What? Let me try that again. Restricted domain is what? We already solved as x is greater than or equal to negative 1/3. Okay. So picking up here, I take this function and I plug it into every x I see. So this has 2 x's. You see that? So what I'm doing is I'm plugging in this function 3. If you want to plug it in there, you can. But either way, I'm plugging in this function algebraically 2 different times. So I would have, instead of an x squared, I'm going to have a square root of 3x plus 1 squared. I'm not using a parenthesis this time just because the bracket itself, the root itself will serve as a parenthesis. Plus 4 times the root of 3x plus 1 plus 5 on the outside. Can we simplify any of this? Yes. What can I simplify? The root and the square cancel out. So we have 3x plus 1. Can I multiply inside the square root? No. Plus 4 root 3x plus 1 plus 5. Can I simplify anything from there? I can add up the positive 1 and the positive 5. Those are like terms. So I'll do this. I'll do the 3x first. What's plus 1 and plus 5? Plus 6, and then we'll add the 4 root 3x plus 1. There's our solution there. That's k of p. Right there, there's our solution. And what are we going to say its restricted domain is? Now here's the deal on this one. We could have got that just from here, but that's not always the case. We could have still seen right there that it was going to have a domain that's not all reals. Okay, now I'm going to go with the calculator. Finish this up just to check our answer. By the way, this range would not be all reals either. This is a parabola. That's a parabola. That will not be all reals. A parabola does not have all real range. So our range will not be all reals either. Let's check out and see what we get. So this time I'm going to change this to k of x. K equals x squared plus 4x plus 5. If you're using the calculator, it doesn't matter what order you put these in, by the way. The calculator, as long as you just need to name them. So the calculator has programmed in what k is equal to and what p is equal to. 3x plus 1 here. So this is the outermost. That means the range. The range is going to come from here. The domain is going to come from here. The greatest the domain could ever be is negative 1/3 to infinity. The greatest the range could ever be is this low point to the high point. What's that low point at? 1. So the greatest the range can be is 1 to infinity. All right, let's find the answer. I need to change this to k of p. So change this to a k, this to a p. There's my value. What do we get as our answer? I forgot. 3x plus 6 plus 4 root 3x plus 1. If I check it out, does that give me the same thing?
Yes,
Yes, it does.
exactly.
Exactly the same thing. That's because, as I was telling you here, that was going to restrict it by itself. Check it out. The domains, they match up. You see how the domain never got cut off any further? It stayed the same. But did the range end up being the same value?
No.
No. At this point here, you can see that we got cut off. We don't have these low values. So the range is a subset. All right, that's all that to show you. You can use technology to help you out in this process. You can use technology. All right, I have one for you to try here. DOL number 3. All right, example 4. Now, what I'm going to do here is I'm going to mix up some representations within and have you solve these. So it says first, the graph of f is shown, and here's the table for g. Let's find f of g of 5. Okay, so here's a question for you. Where does the 5 go first? 5 is going to go into g, and it's going to produce something. Let's go find what 5 produces. So go to g's equation. Here's g. And you're plugging in 5 into g's equation. That means you need to x of 5. So you see this x right here? This is for part A. I'm going to do this just because, well, I'll just leave it like that for now. I'll do red. So what does 5 produce into g's equation? -2. We got a -2. So what am I going to do with this -2? F. So you go to F, and it's this x value. So you go to this x-axis here. We add x and y. And you find -2. Here's -2 right there. You see that? When I plug that in, what do I produce? This produces a +2. So that's how it works. Is that produces 2. Let me actually not circle that. That way it looks neater and the same. So this value, this answer would be +2. Out came a 2 whenever we did this. Does that make sense? So again, they can mix up representations. It's still the same work. What about 8? So we go to the graph first. Here's 8. And so what's the y value produced at 8? -1. So I just produced a -1. So I need to plug in my -1 into g. Here's -1, and what do we get? 3. Good. So the answer is 3. I'm gonna let you try one more. And I'm not going to guide you through this one as much. -4 goes into g. And so when you plug in a -4, what do we get? Pi. Now, what do I do with the pi? Now, here's the question. Do we need a round? No. You just go to pi. And it doesn't matter because this is constant. So wherever pi is, let's just say it's right here. Let's just say that pi is coming somewhere in there. You go straight up, and what y value will you get? Because this is a constant line. It's not hard for us. You see what I'm doing here? Just saying pi is somewhere right in there. If it's 3.14, it's somewhere in there. What do you get for your y? You get 1. So we just got a 1. What do I do with 1? So now I go to 1. Here's a 1. And that produces this point. And what do we get there? +4. 4 would be your answer. All right, your final DOL of the day.